Well, welcome back to our course, Computer Organization and Architecture. So we're going to continue on in our section of looking at things in the central processing unit. And so this is the third of four lectures that we're going to be looking at. And so this is going to be focusing on instruction level, parallelism, and superscalar processors. So just a summary, we'll get into this and then we'll come back to this and hopefully it'll be a lot more clear as a result of what we've gone over. First, we'll talk about superscalar versus super pipelined. We'll talk about the variety of design issues that need to be addressed with this. We'll look at the Intel Core microarchitecture for doing this, and then we'll look at two ARM architectures, the Cortex A8 and the Cortex M3. Okay, let's go ahead and continue. So the term superscalar was first coined in 1987, refers to a machine that is designed to improve the performance of the execution of scalar instructions. In most applications, the bulk of the operations are on scalar quantities. Accordingly, the superscalar approach represents the next step in the evolution of high-performance general-purpose processors. The essence of the superscalar approach is the ability to execute instructions independently and concurrently in different pipelines. This concept can be further exploited by allowing instructions to be executed in an order different from the program order. So here in figure 18.1, it compares in general terms of the scalar and superscalar approaches. In traditional scalar organizations, there is a single pipeline function unit for integer operation and one for floating point operation. Parallelism is achieved by enabling multiple instructions to be at different stages of the pipeline at once. In the superscalar organization, there are multiple functional units, each of which is implemented as a pipeline. Each individual functional unit provides a degree of parallelism by virtue of its pipeline structure. The use of multiple functional units enables the processor to execute streams of instructions in parallel, one stream for each pipeline. It is the responsibility of the hardware in conjunction with the compiler to assure that the parallel execution does not violate the intent of the program. Now here in figure 18.2, it provides an additional detail of typical organizations for superscalar pipeline processing. You can compare this with figure 1716. The L1 cache is divided into instruction and data. Groups of instructions are fetched into an instruction buffer. The instruction decode stage involves, at minimum, determining the opcode and operand specifiers. This stage also usually involves detection of inter-instruction dependencies among the group of instructions that have been fetched but not yet dispatched. This stage selects instructions to be issued in the next instruction cycle and sends them to the issue window. The issue window holds all decoded instructions of issue in the next cycle. The width of the issue window corresponds to the degree of superscaling. So define issue rate as the number of instruction issued per instruction cycle. Then for superscalar machine, the maximum issue rate equals the width of the issue window. The mean issue rate depends on the occurrence of pipeline hazards and constraints and the issue policies that are based on these hazards and constraints. The design objective is to achieve an issue rate of well above one instruction per cycle, one instruction per instruction cycle, and as close as reasonable to the maximum issue rate. The issue window is followed by a set of reservation stations with instructions being issued from the issue window as reservation station capacity becomes available. The concept of a single reservation station was introduced in chapter 16. With a superscalar architecture, there are multiple reservation stations, one for each pipeline. Each reservation station is essentially a set of input registers that are used to buffer operations and operands for a functional unit. The purpose of the reservation station is to relieve a bottleneck at the instruction decode, that is the ID stage. The ID can issue an instruction as soon as the functional unit is available and hazards are resolved. The problem this creates is the ID stage cannot receive a new instruction until the previous instruction has been issued. The reservation stations provide a buffer that enables the ID stage to issue instructions as soon as possible. Then the reservation station will dispatch each instruction to its functional unit when the latter is available. The reorder buffer results until it is safe to store the results in memory or a register and program order. When an instruction is complete and can be finalized, it is either written back to the register file or the results forwards to the reservation stations. Many researchers have investigated superscalar-like processors, and the research indicates that some degree of performance improvements is possible. Here we're showing in table 18.1 the reported performance advantages. So it can range anywhere from close to 2 to up to 8. The difference in the results arise from differences both in the hardware of the simulated machines and in the application being simulated. An alternative approach is to achieving greater performance is referred to super pipelining, term that was coined back in 1988. Super pipelining divides the pipeline into a greater number of smaller stages in order to clock it at a higher frequency. There is still only one pipeline, but by increasing the number of stages, we increase its temporal parallelisms. It is working on more instructions at the same time. The use of a very deep, very high-speed pipeline for instruction processing is called super pipeline. We have seen one example of this approach when we talked about the MIPS R4000. Figure 18.3, which we're showing here, compares the two approaches. The upper part of the diagram illustrates an ordinary pipeline used as a baseline for comparison. The base pipeline issues one instruction per clock cycle and can perform one pipeline stage per clock cycle. The pipeline has 4 stages: instruction fetch, operation decode, operation execute, and write back the result. The execution stage is crosshatched for clarity. Note that although several instructions are executing concurrently, only one instruction is in its execution state at any one time. The next part of the diagram shows a super pipeline implementation that is capable of performing 2 pipeline stages per clock cycle. An alternative way of looking at this is the functions performed in each stage can be split into non-overlapping parts, and each can execute in half a clock cycle. A super pipeline implementation that behaves in this fashion is said to be of degree 2. Finally, the lower part of the diagram shows a superscalar implementation capable of executing 2 stages of each stage in parallel. High-degree super pipeline and superscalar implementations are, of course, possible. Both the super pipeline and superscalar approaches depicted in the figure we're showing here, 18.3, have the same number of instructions executing at the same time in the steady state. The super pipeline approach falls behind the superscalar approach at the start of the program and at each branch target. The superscalar approach depends on the ability to execute multiple instructions in parallel. The term instruction level parallelism refers to the degree to which, and on average, the instructions of a program can be executed in parallel. A combination of compiler-based optimization and hardware techniques can be used to maximize instruction level parallelism. Before examining the design techniques used in superscalar machines to increase instruction level parallelisms, we need to look at the fundamental limitations to parallelisms with which the system must cope. And so we'll consider 5, the true data dependency, procedure dependency, resource conflicts, output dependency, and anti-dependency. So consider the following sequence, add EAX, comma, ECX, which is what it does. It loads a register EAX with the contents of ECX plus the contents of EAX. Next, we have move EBX, comma, EAX. This loads EBX with the contents of EAX. The second instruction can be fetched and decoded, but cannot execute until the first instruction executes. The reason is that the second instruction needs data produced by the first instruction. This situation is referred to as true data dependency, also called flow dependency or read after write dependency. Figure 18.4, which we're showing here, illustrates this dependency. In a superscalar machine of degree 2 with no dependency, 2 instructions can be fetched and executed in parallel. If there is a data dependency between the first and second instructions, then a second instruction is delayed as many clock cycles as required to remove the dependency. In general, any instruction must be delayed until all of its input values have been produced. In a simple pipeline, such as illustrated in the upper part of figure 18.3, the aforementioned sequence of instructions would cause no delay. However, considering the following, in which one of the loads is from memory rather than from a register. So if we have move EAX, comma EEF, it loads a register with the contents of the effective memory address EFF. So, and then move EBX, comma EAX, that would load EBX with the contents of EAX. A typical RISC processor takes 2 or more cycles to perform a load from memory when the load is a cache hit. It can take tens or even hundreds of cycles for a cache miss on all cache levels because of the delay of an off-chip memory access. One way to compensate for this delay is for the compiler to reorder instructions so that one or more subsequent instructions that do not depend on the memory load can begin flowing through the pipeline. The scheme is less effective in the case of a superscalar pipeline. The independent instructions execute during the load are likely to be executed on the first cycle of the load, leaving the processor with nothing to do until the load completes. As was discussed in chapter 14, the presence of branches in an instruction sequence complicates the pipeline operation. The instructions following a branch, taken or not taken, have a procedural dependency on the branch and cannot be executed until the branch is executed. Figure 18.4, which we're showing here, illustrates the effects of a branch on a superscalar pipeline of degree 2. As we have seen, this type of procedural dependency also affects a scalar pipeline. The consequence for a superscalar pipeline is more severe because a greater magnitude of opportunity is lost with each delay. If a variable length instructions are used, then another sort of procedural dependency arises. Because the length of any particular instruction is not known, it must be at least partially decoded before the following instruction can be fetched. This prevents the simultaneous fetching required in a superscalar pipeline. This is one of the reasons that superscalar techniques are more readily applicable to RISC or RISC-like architectures with its fixed instruction length. A resource conflict is a competition of 2 or more instructions for the same resource at the same time. Examples of resources include memories, cache, buses, register file ports, and functional units like the arithmetic unit adder. In terms of the pipeline, a resource conflict exhibits similar behavior to data dependency. So we can keep that in mind. And so there are some differences, however. For one thing, resource conflicts can be overcome by duplication of resources, whereas a true data dependency cannot be eliminated. Also, when an operation takes a long time to complete, resource conflicts can be minimized by pipelining the appropriate functional unit. Well, let's talk about design issues. So one study that the text refers to, it makes an important distinction between the two related concepts of instruction level parallelism and machine parallelism. Instruction level parallelism exists when instructions in a sequence are independent and thus can be executed in parallel by overlapping. The degree of instruction level parallelism is determined by the frequency of true data dependencies and procedural dependencies in the code. These factors in turn are dependent on the instruction set architecture and on the application. Instruction level parallelism is also determined by what is referred to as an operation latency, that is the time until the result of an instruction is available for use as an operand in a subsequent instruction. The latency determines how much of a delay a data or procedural dependency will cause. Machine parallelism is a measure of the ability of the processor to take advantage of instruction level parallelism. Machine parallelism is determined by the number of instructions that can be fetched and executed at the same time. That is the number of parallel pipelines, and by the speed and sophistication of the mechanism that the processor uses to find independent instructions. Both instruction level and machine parallelisms are important factors in enhancing performance. A program may not have enough instruction level parallelisms to take full advantage of machine parallelism. The use of a fixed length instruction set architecture as a risk enhances instruction level parallelism. On the other hand, limited machine parallelisms will limit performance no matter what the nature of the program. So let's talk about instruction issue policy. As was mentioned, machine parallelism is not a simple matter of having multiple instances of each pipeline stage. The processor must be able to identify instruction level parallelism and orchestrate the fetching, decoding, and execution of instructions in parallel. One of the references from the text uses the term instruction issue to refer to the process of initiating instruction execution in the processor's functional units, and the term instruction issue policy is referred to the protocol used to issue instructions. In general, we can say that instruction issue occurs when instructions move from the decode stage of the pipeline to the first and execute stage of the pipeline. In essence, the processor is trying to look ahead of the current point of execution to locate instructions that can be brought into the pipeline and executed. Three types of ordering are important in this regard: the order in which the instructions are fetched, the order in which the instructions are executed, and the order in which the instructions update the content of the registers and memory location. The more sophisticated the processor, the less it is bound by a strict relationship between these orderings. To optimize utilization of the various pipeline elements, the processor will need to alter one or more of these orderings with respect to the ordering to be found in a strict sequential execution. The one constraint on the processor is the result must be correct. Thus, the processor must accommodate the various dependencies and conflicts discussed earlier. In general terms, we can group superscalar instruction issues policies into the following categories. In order issue with in order completion, in order issue with out of order completion, and out of order issue with out of the order completion. The simplest instruction issue policy is to issue instructions in the exact order that would be achieved by sequential order. So that would be in order issue, what we would do in sequential execution, and to write results in the same order in order completion. Not every scalar pipeline follows such a simple-minded policy. However, it is useful to consider this policy as a baseline for comparing more sophisticated approaches. Figure 18.5a gives an example of this simple policy. So it's showing an in-order issue and in-order completion. We assume a superscalar pipeline capable of fetching and decoding 2 instructions at a time, having 3 separate functional units. For example, 2 integer arithmetic and 1 floating point arithmetic, and having 2 instances of a write-back pipeline stage. The example assumes the following constraints on a 6 instruction code fragment. I1 requires 2 cycles to execute. I3 and I4 conflict with the same functional unit. I5 depends on the value produced by I4, and I5 and I6 conflict for a functional unit. Instructions are fetched 2 at a time and passed to the decode unit. Because instructions are fetched in pairs, that the next 2 instructions must wait until the pair of decode pipeline stages have cleared. To guarantee in-order completion when there is a conflict for functional unit or when a functional unit requires more than 1 cycle to generate a result, the issuing of instructions temporarily stalls. In this example, the elapsed time from decoding the first instruction to writing the last instruction is 8 cycles. For out-of-order completion, it is used in scalar RISC processors to improve the performance of instructions that require multiple cycles. Figure 18.5b illustrates its use on a superscalar processor. Instruction I2 is allowed to run to completion prior to I1. This allows I3 to be completed earlier with the net result of saving 1 cycle. With out-of-order completion, any number of instructions may be in the execution stage at any one time, up to the maximum degree of machine parallelism across all functional units. Instructions issuing is stalled by a resource conflict, a data dependency, or a procedural dependency. In addition to the aforementioned limitation, a new dependency, which we referred to earlier as the output dependency, which is also called the write after write dependency, arises. Out-of-order completion requires more complex instruction issue logic than in-order completion. In addition, it is more difficult to deal with instruction interrupts and exceptions. When an interrupt occurs, instruction execution at the current point is suspended to be resumed later. The processor must assure that the resumption takes into account that at the time of interruption, instructions ahead of the instruction that caused the interruption may already have completed. Okay, well, let's talk about the organization for out-of-order issues with out-of-order completion. Within order issue, the processor will only decode instructions up to the point of dependency or conflict. No additional instructions are decoded until the conflict is resolved. As a result, the processor cannot look ahead of the point of conflict to subsequent instructions that may be independent of those already in the pipeline, and that may be usefully introduced into the pipeline. To allow out-of-order issue, it is necessary to decouple the decode and execute stages of the pipeline. This is done with a buffer referred to as an instruction window. With this organization, after a processor has finished decoding an instruction and is placed in the instruction window, as long as this buffer is not full, the processor can continue to fetch and decode new instructions. When a functional unit becomes available in the execute stage, an instruction from the instruction window may be issued to the execute stage. Any instruction may be issued provided that one, it needs the particular functional unit that is available, and two, no conflicts of dependencies block this instruction. What we're showing here in figure 18.6 suggests this organization. The results of this organization is that the processor has a look-ahead capability, allowing it to identify independent instructions that can be brought into the execute stage. Instructions are issued from the instruction window with little regard for their original program order. As before, the only constraint is the program execution behaves correctly. Figure 18.5c illustrates this policy. During each of the first 3 cycles, 2 instructions are fetched into the decode stage. During each cycle, subject to the constraints of the buffer size, 2 instructions are moved from the decode stage to the instruction window. In this example, it is possible to issue instruction I16 ahead of I5. Recall that I5 depends on I4, but I6 does not. Thus, one cycle is saved in both. The execute and write back stages and the end-to-end savings compared with 18.5b is one cycle. The instruction window is depicted in 18.5c to illustrate its role. However, this window is not an additional pipeline stage. An instruction being in the window simply implies that the processor has sufficient information about that instruction to decide when it can be issued. The out-of-order issue, out-of-order completion policy is subject to the same constraints described earlier. An instruction cannot be issued if it violates a dependency or conflict. The difference is that more instructions are available for issuing, reducing the probability that a pipeline stage will have to stall. In addition, a new dependency, which we referred earlier to as the anti-dependency, which is also called the write after read dependency, arises. So when out of order instruction issuing and or out of order instruction completions are allowed, we have seen this gives rise to the possibility of a WAW dependencies and WAR dependencies. These dependencies differ from RAW data dependencies and resource conflicts, which reflect the flow of the data through a program and the sequence of execution. WAW dependencies and WAR dependencies, on the other hand, arise because the value in registers may no longer reflect the sequence of values dictated by the program flow. When instructions are issued in sequence and complete in sequence, it is possible to specify the contents of each register at each point in the execution. When out-of-order techniques are used, the value in registers cannot be fully known at each point in time just from a consideration of the sequence of instructions dictated by the program. In effect, values are in conflict for the use of registers, and the processor must resolve those conflicts by occasionally stalling a pipeline stage. Anti-dependencies and output dependencies are both examples of storage conflicts. Multiple instructions are competing for the use of the same resource locations, generating pipeline constraints that retard performance. The problem is made more acute when registers optimization techniques are used, which is discussed in chapter 15. Because these compiler techniques attempt to maximize the use of registers, hence maximizing the number of storage conflicts. One method for coping with these types of storage conflicts is based on the traditional resource conflict solution, duplication of resources. In this context, the technique is referred to as register renaming. In essence, registers are allocated dynamically by the processor hardware, and they are associated with the values needed by the instructions at various points in time. When a new register value is created, that is, when the instruction executes that has a register as a destination operand, a new register is allocated for that value. Subsequent instructions that access this value as a source operand in that register must go on through a renaming process. The register references in those instructions must be revised to refer to the register containing the needed value. Thus, the same original register reference in several different instructions may refer to different actual registers if different values are intended. The register reference without the subscript refers to the logical register reference found in the instruction. The register reference with the subscript refers to a hardware register allocated to hold a new value. When a new allocation is made for a particular logical register, subsequent instructions references to that logical register as a source operand are made to refer to the most recently allocated hardware register that is recent in terms of the program sequence of instructions. All right, well, let's continue on with various ways of doing speed up. And here we're talking about speed up of various machine organizations without procedural dependencies. So in the previous discussion, we looked at 3 hardware techniques that can be used in a superscalar processor to enhance performance: duplication of resources, out of order issue, and renaming. One study in the textbook illuminates the relationship among these techniques, and it reported its results. It published its results. The study made use of a simulation that modeled a machine with the characteristics of a MIPS R2000 augmented with various superscalar features. A number of different programs sequences were simulated. Figure 18.7, which we're showing here, shows the results. In each of these graphs, the vertical axis corresponds to the mean speedup of the superscalar machine over the scalar machine. The horizontal axis shows the results for 4 alternative processor organizations. The base machine does not duplicate any of the functional units, but it can issue instructions out of order. The second configuration duplicates the load/store functional unit that accesses a data cache. The third configuration duplicates the arithmetic logic unit, and the fourth configuration duplicates both the load/store and the arithmetic logic unit. In each graph, results are shown for instruction window sizes of 8, 16, and 32 instructions, which dictates the amount of look ahead the processor can do. The difference between the 2 graphs is that the second register renaming is allowed. This is equivalent to saying that the first graph reflects a machine that is limited by all dependencies, whereas the second graph corresponds to a machine that is limited only by true dependencies. The 2 graphs combined yield some important conclusions. The first is that it is probably not worthwhile to add functional units without register renaming. There is some slight improvement in performance, but at the cost of increasing hardware complexity. With register renaming, which eliminates anti-dependencies and output dependencies, noticeable gain are achieved by adding more functional units. Note, however, that there is a significant difference in the amount of gain achievable between using an instruction window of 8 versus a larger instruction window. This indicates that if the instruction window is too small, data dependencies will prevent effective utilization of the extra functional units. The processor must be able to look quite far ahead to find independent instructions to utilize the hardware more fully. Any high-performance pipeline machine must address the issue of dealing with branches. For example, the Intel 8486 addressed the problem by fetching both the next sequential instruction after a branch and speculatively fetching the branch target instruction. However, because there are two pipeline stages between the prefetch and the execution, the strategy incurs a two-cycle delay when the branch gets taken. With the advent of the RISC machines, the delayed branch strategy was explored. This allows the processor to calculate the result of conditional branch instructions before any unusable instructions have been prefetched. With this method, the processor always executes the single instruction that immediately follows the branch to keep the pipeline full while the processor fetches a new instruction stream. With the development of superscalar machines, the delayed branch strategy has less appeal. The reason is that multiple instructions need to execute in the delay slot, raising several problems relating to the instruction dependencies. Thus, superscalar machines have returned to pre-RISC techniques of branch prediction. Some, like the PowerPC 601, used a simple static branch prediction technique. More sophisticated processors, such as the PowerPC 620 and the Pentium 4, use dynamic branch prediction based on branch history analysis. So now let's illustrate the conceptual depiction of a superscalar processing. So we're now in a position to provide an overview of superscalar execution of programs. This is illustrated in figure 18.8, which we're showing. The program to be executed consists of a linear sequence of instructions. This is the static program as written by a programmer or generated by the compiler. The instruction fetch stage, which includes branch prediction, is used to form a dynamic stream of instructions. This stream is examined for dependencies, and the processor may remove artificial dependencies. The processor then dispatches the instructions into a window of execution. In this window, instructions no longer form a sequential stream, but are structured according to their true data dependencies. The processor executes each instruction in an order determined by the true data dependencies and hardware resources available. Finally, instructions are conceptually put back into their sequential order and the results are recorded. The final step mentioned in this preceding, what we just discussed, is referred to as committing or retiring the instruction. The step is needed for the following reason. Because of the use of multiple parallel pipelines, instructions may complete in an order different from that shown in the static program. Further, the use of branch prediction and speculative execution means that some instructions may complete execution and then must be abandoned because the branch they represented is not taken. Therefore, permanent storage and program visible registers cannot be updated immediately when instructions complete execution. Results must be held in some sort of temporary storage that is usable by dependent instructions and then made permanent when it is determined that the execution model would have executed the instruction. So let's think a little bit more about superscalar implementation. Based on our discussion so far, we can now make some general comments about the processor hardware required for the superscalar approach. And one of the references in the text refer to these key elements. First, the instruction fetch strategies that simultaneously fetch multiple instructions, often by predicting the outcome and fetching beyond conditional branch instructions. These functions require the use of multiple pipeline fetch and decode stages in branch prediction logic. Logic for determining true dependencies involving register values and mechanisms for communicating these values where they are needed during execution. We have mechanisms for initiating or issuing multiple instructions in parallel. We have resources for parallel execution of multiple instructions, including multiple pipeline functional units and memory hierarchies capable of simultaneously servicing multiple memory references. And we have mechanisms for committing the process state in correct order. So although the concept of superscalar design is generally associated with the RISC architecture, the same superscalar principles can be applied to a CISC machine. Perhaps the most notable example of this is the Intel X86 architecture. The evolution of the superscalar concepts in the Intel line is interesting to note. The 386 is a traditional CISC non-pipeline machine. The 486 introduced the first pipelined x86 processor, reducing the average latency of the integer operations from between 2 and 4 cycles to 1 cycle, but still limited to executing a single instruction each cycle with no superscalar elements. The original Pentium had a modest superscalar component consisting of the use of 2 separate integer execution units. The Pentium Pro introduced a full-blown superscalar design with out-of-order execution. Subsequent x86 models have refined and enhanced a superscalar design. So figure 18.9, which we're showing here, shows the current version of the x86 pipeline architecture. Intel refers to a pipeline architecture as microarchitecture. The microarchitecture underlines and implements the machine's instruction set architecture. The microarchitecture is referred to as the Intel Core microarchitecture. It is implemented on each processor core in the Intel Core 2 and Intel Xeon processor families. There is also an enhanced Intel Core microarchitecture. One key difference between the two microarchitectures is that the enhanced Intel Core microarchitecture provides a third level of cache. So table 18.2 shows some of the parameters and performance characteristics of the cache architecture. All of the caches use a write-back update policy. When an instruction reads data from a memory location, the processor looks for the cache line that contains this data in the caches and main memory in the following order. 1, L1 data cache of the initiating core, 2, L1 data cache of the other cores, and L2 cache, and 3, system memory. The cache line is taken from the L1 data cache of another core only if it is modified, ignoring the cache line available or state in the L2 cache. Table 18.2b shows the characteristics of fetching the first 4 bytes of the different localities from the memory cluster. The latency column provides an estimate of access latency. However, the actual latency can vary depending on the load of cache, memory components, and their parameters. The pipeline of the Intel Core microarchitecture contains an in-order issue front end that fetches instruction streams from memory with 4 instruction decoders to supply decoder instructions to the out-of-order execution core. Each instruction is translated into 1 or more fixed-length RISC instructions known as micro operations or micro-ops. An out-of-order superscalar execution core that can issue up to 6 micro-ops per cycle and reorder micro-ops to execute as soon as resources are ready and execution resources are available. An in-order retirement unit has an in-order retirement unit that ensures the results of execution of micro-ops are processed and architectural states and the processor registers are set. Our register set are updated according to the original program order. So in effect, the Intel Core microarchitecture implements a CISC instruction set architecture on a RISC microarchitecture. The inner RISC microops pass through a pipeline with at least 14 stages. In some cases, the microops requires multiple execution stages, resulting in an even longer pipeline. This contrasts with the 5-stage pipeline that we had in figure 1621, used on earlier Intel x86 processors and the Pentium. So you are welcome to pause the recording when you like and to think about this, but you can see there's a lot of detailed work that's being done as Intel is using things that normally would be used for a RISC processor on a CISC architecture. And so here we're talking about cache parameters and load store performance. And if we just back up, here we can see these types of caches that are supporting this. We can see the various types of units that are available for the store and load. And so those are some things to be thinking about. So the front end needs to supply decoded instructions, that is microops, and sustain the stream to a 6-issue wide out-of-order engine. It consists of 3 major components: branch prediction unit, the BPU, the instruction fetch and predecode unit, and instruction queue and decode unit. For the branch prediction unit, this unit helps the instruction fetch unit fetch the most likely instruction to be executed by predicting the various branch types, that is the conditional, indirect, direct, call, and return. The BPU uses dedicated hardware for each branch type. Branch prediction enables the processor to begin executing instructions long before the branch outcome is decided. The microarchitecture uses a dynamic branch prediction strategy based on the history of recent executions of branch instructions. There is a branch target buffer of BTB, and it's maintained that caches information about recent encountered branch instructions. When a branch instruction is encountered in the instruction stream, the BTB is checked. If an entry already exists in the BTB, then the instruction unit is guided by the history information for that entry in determining whether to predict that the branch is taken. If a branch is predicted, then the branch destination address associated with the entry is used for prefetching the branch target instructions. One of the instructions is executed. Once the instruction is executed, the history portion of the appropriate entry is updated to reflect the result of the branch instruction. If this instruction is not represented in the BTB, then the address of the instruction is loaded into an entry in the BTB. If necessary, an older entry is deleted. The description of the preceding 2 paragraphs, the things that we just were mentioning here, following along in the textbook if you want to do that. In general terms, the branch prediction strategy used on the original Pentium model, as well as the later Pentium models, includes current Intel models. However, in the case of the Pentium, a relatively simple 2-bit history scheme is used. The later models have much longer pipelines, 14 stages for the Intel Core microarchitecture compared with 5 stages for the Pentium. And therefore, the penalty for mispredicting is greater. Accordingly, the later models use a more elaborate branch prediction scheme with more history bits to reduce the misprediction rate. Conditional branches that do not have a history in the BTB are predicted using a static prediction algorithm according to the following rules. For branch addresses that are not instruction pointers, relative predict taken if the branch is a return and not taken otherwise. For IP related backward conditional branching taken, this rule reflects the typical behavior of loops. And for IP related forward conditional branch prediction not taken. The instruction fetch unit comprises the instruction translation look-aside buffer, ITLB, and instruction prefetcher, the instruction cache, and the predecoder logic. Instruction fetch is performed from an L1 instruction cache when an L1 cache miss occurs. The in-order front end feeds new instructions into the L1 cache from the L2 cache 64 bytes at a time. As a default, instructions are fetched sequentially so that each L2 cache line fetch includes the next instruction to be fetched. Branch prediction via the branch prediction unit may alter the sequential fetch operation. The ITLB translates the linear IP address, giving it into physical addresses needed to access the L2 cache. Static branch prediction in the front end is used to determine which instruction to fetch next. The pre-code unit accepts the 16 bytes from the instruction cache or prefetch buffers and carries out the following tasks. It determines the length of the instructions, it decodes all prefixes associated with instructions, and marks various properties and instructions for the decoder. For example, is branch. The precoder can write up to 16 instructions per cycle into the instruction queue. If a fetch contains more than 6 instructions, the predecoder continues to decode up to the 6 instructions per cycle until all instructions in the fetch are written to the instruction queue. Subsequent fetches can only enter predecoding after the current fetch completes. Fetch instructions are placed in an instruction queue. From there, the decode unit scans the bytes to determine instruction boundaries. This is a necessary operation because of the variable length of x86 instructions. The decoder translates each machine instruction from 1 to 4 micro-ops, each of which is a 118-bit RISC instruction. Note for comparison, the most pure RISC machines have an instruction length of just 32 bits. The longer micro-op length is required to accommodate the more complex x86 instructions. Nevertheless, the micro-ops are easier to manage than the original instructions from which they were derived. A few instructions require more than 4 micro-ops. These instructions are transferred to microcode ROM, which contain the series of micro-ops, 5 or more that is, associated with a complex machine instruction. For example, the string instruction may translate into a very large, evens hundreds of repetitive sequence of micro-ops. Thus, the microcode ROM is a microprogram control unit, and in this sense is discussed in part 6, and so that'll be a later topic we'll circle back to. The resulting micro-op sequence is delivered to the rename/allocator module. This part of the processor records micro-ops to allow them to execute as quickly as their input operands are ready. The allocate stage allocates resources required for execution. It performs the following functions. The needed resource, such as the register, is unavailable for one of the 3 micro-ops arriving at the allocator during a clock cycle. The allocator stalls the pipeline. The allocator allocates a record buffer, ROB, entry, which tracks the completion status of one of the 128 micro-ops that could be in the processor at any time. The allocator allocates one of the 128 integer or floating point register entries for the result data value of the micro-op and possibly a load or store buffer used to track one of the 48 loads or 24 stores in the machine pipeline. The allocator allocates an entry in one of the two micro-op queues in front of the instruction schedulers. So let's talk a little bit more about the ROB, the reorder buffer. The ROB is a circular buffer that can hold up to 128 micro-ops and also contain the 128 hardware registers. Each buffer entry consists of the following fields: state. It indicates whether the micro-op is scheduled for execution, has been dispatched for execution, or has completed execution, is ready for retirement. Memory address, the address of the Pentium instruction that generated the micro-ops, the actual operation. The alias register, it is the micro-op reference, one of the 16 architectural registers. This entry redirects that reference, so one of the 128 hardware registers. And micro-ops enter the ROB in order. Micro-ops are then dispatched from the ROB to the dispatch/execute unit out of order. The criterion for dispatch is the appropriate execution unit and all necessary data items required for this micro-op are available. Finally, micro-ops are retired from the ROB in order. To accomplish in-order retirement, micro-ops are retired oldest first after each micro-op has been designated as ready for retirement. The naming stage remaps references to the 16 architectural registers. That is the 8 floating point registers plus the EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP into a set of 128 physical registers. These stage removes false dependencies caused by a limited number of architectural registers while preserving the true data dependencies read and write. After resource allocations and register renaming, micro-ops are placed in one of two micro-op queues when they are held until there is room in the scheduler. One of the two queues is for memory operation, that is for load and stores, and the other for micro-ops that do not involve memory references. Each queue obeys a FIFO, that is first in, first out, discipline, but no order is maintained between queues. That is, a micro-op may be read out of the queue out of order with respect to the micro-ops in the other queue. This provides greater flexibility to the schedulers. The schedulers are responsible for retrieving micro-ops from the micro-op queues and dispatching these for instruction. Each scheduler looks for micro-ops and whose status indicates that the micro-ops has all of its operands. If the execution unit needed by that micro-op is available, then the scheduler fetches the micro-op and dispatches it to the appropriate execution unit. Up to 6 micro-ops can be dispatched in one cycle. If more than one micro-op is available for a given execution unit, then the scheduler dispatches them in sequence from the queue. This is a sort of FIFO, first in, first out discipline that favors in-order execution, but by the time the instruction stream has been so rearranged by dependencies and branches that it is subsequently out of order. 4 ports attach the schedulers to the execution units. Port 0 is used for both integer and floating point instructions, with the exception of simple integer operation and the handling of branch mispredictions, which are allocated to port 1. In addition, MMX execution units are allocated between these 2 ports. The remaining ports are for memory, loads, and stores. The integer and floating point register files are the source for pending operations by the execution unit. The execution units retrieve values from the registers from files as well as the L1 data cache. A separate pipeline stage is used to compute flags, for example, 0 or negative. These are typically the inputs to a branch instruction. A subsequent pipeline stage performs branch checking. This function compares the actual branch results with the prediction. If a branch prediction turns out to have been wrong, then there are micro operations in various stages of processing that must be removed from the pipeline. The proper branch destination is then provided to the branch predictor during a drive stage, which restarts the whole pipeline from the new address, from the new target address. Okay, well, let's now talk about some specific examples here for a couple ARM models here. So first, we'll talk about the ARM Cortex-A8. So recent implementations of the ARM architecture have seen the introduction of superscalar techniques in the instruction pipeline. In this section, we focus on the ARM Cortex-A8, which provides a good example of a RISC-based superscalar design. The Cortex-A8 is the ARM family of processors that ARM refers to as application processors. An ARM application processor is an embedded processor running complex operations systems for wireless, consumer, and imaging applications. The Cortex-A8 targets a wide variety of mobile and consumer applications, including mobile phones, set-top boxes, gaming consoles, automobile navigation, and entertainment systems. Figure 1810, which are shown here, shows a logical view of the Cortex-A8 architecture, emphasizing the flow of instructions among functional units. The main instruction flow is through 3 functional units that implement a dual in-order issue 13-stage pipeline. The Cortex designers decided to stay with the in-order issue to keep additional power requirements to a minimum. Out-of-order issue and retire can require extensive amounts of logic consuming extra power. In this figure 1811, it shows the details of the main Cortex-A8 pipeline. There is a separate unit for an SIMD, a single instruction multiple data, that implements a 10-stage pipeline. So you can pause the video and look over that in more detail if you like, but I'll continue to press forward. Let's talk about the instruction fetch unit. The instruction fetch unit predicts the instruction streams, fetches instructions from the L1 instruction cache, and places the fetch instructions into a buffer for consumption by the decoder pipeline. The instruction fetch unit also includes the L1 instruction cache. Because there can be several unresolved branches in the pipeline, instruction fetches are speculative, meaning there is no guarantee that they are executed. A branch or exceptional instruction in the code stream can cause a pipeline flush, discarding the currently fetched instructions. The instruction fetch unit can fetch up to 4 instructions per cycle and goes through the following stages. F0, the address generation unit, the AGU, generates a new virtual address. Normally, this address is the next address sequentially from the preceding fetch address. This address can also be a branch target address provided by a branch prediction for a previous instruction. F0 is not counted as part of the 13-stage pipelines because ARM processors have traditionally defined instruction cache access as the first stage. Then there's F1, the calculated address is used to fetch instructions from the L1 instruction cache. In parallel, the fetch address is used to access the branch prediction arrays to determine if the next fetch address should be based on branch predictions. Then there's F3. The F3 instruction data are placed into the instruction queue. If an instruction results in branch prediction, the new target address is sent to the address generation unit. To minimize the branch penalties typically associated with a deeper pipeline, the Cortex-A8 processor implements a two-level global history branch predictor consisting of the branch target buffer, the BTB, and the global history buffer, the GHB. These data structures are accessed in parallel with instruction fetches. The BTB indicates whether or not the current fetch address will return a branch instruction and its branch target address. It contains 512 entries. On a hit in the BTB, a branch is predicted and the GHB is accessed. The GHB consists of 4096 2-bit counters that encode the strength and direction information of the branches. The GHB is indexed by 10-bit history of the direction of the last 10 branches encountered and 4 bits of the PC, the program counter. In addition to the dynamic branch predictor, a return stack is used to predict subroutine return addresses. The result stack has 8 32-bit entries that store the link register value in R14 and the arm or thumb state of the calling function. When a return type instruction is predicted taken, the return stack provides the last pushed address and state. The instruction fetch unit can fetch and queue up to 12 instructions. It issues instructions to the decode unit 2 at a time. The queue enables the instruction fetch unit to prefetch ahead of the rest of the integer pipeline and build up a backlog of instructions ready for decoding. The instruction decoder unit decodes and sequences all ARM and thumb instructions. As remember, thumb is this reduced set of instructions that we talked about previously, but 16-bit instructions that cherry pick certain bits and put it into a 32-bit format. It has a dual pipeline structure called pipe 0 and pipe 1 so that 2 instructions can process through the unit at a time. When 2 instructions are issued from the instruction decode pipeline, pipe 0 will always contain the older instructions in program order. This means that if the instruction in pipe 0 cannot issue, then the instruction in pipe 1 will not issue. All issued instructions progress in order down the execution pipeline with results written back into the register file at the end of the execution pipeline. This in-order instruction issue and retire prevents WAR hazards and keeps tracking WAW hazards and recovery from flush conditions straightforward. Thus, the main concerns of the instruction decode pipeline is the prevention of RAW hazards. So each instruction goes through 5 stages of processing. D0, thumb instructions are decompressed into 32-bit ARM instructions. Preliminary decode function is performed. D1, the instruction decode function is complete. D2, the stage writes instructions into and reads instructions from the pending/replay queue structure. D3, the stage contains the instructions scheduling logic. A scoreboard predicts register availability using static scheduling techniques. Hazard checking is also done at this stage. D4, perform the final decode for all the control signals required by the integer execute and load/store units. In the first 2 stages, the instruction types, the source and destination operands, and resource requirements for the instructions are determined. A few less commonly used instructions are referred to as multi-cycle instructions. The D1 stage breaks these instructions down into multiple instruction opcodes that are sequenced individually through the execution pipeline. The pending queue serves two purposes. First, it prevents a stall signal from D3 from rippling any further up the pipeline. Second, by buffering the instructions, there should always be two instructions available for the dual pipeline. In the case where only two instructions, in the case when only one instruction is issued, the pending queue enables two instructions to be processed down the pipeline together, even if they were originally sent from the fetch unit in different cycles. The replay operation is designed to deal with the effect of the memory system on instruction timing. Instructions are statistically scheduled in the D3 stage based on the prediction of when the source operand will be available. Any stall from the memory system can result in the minimum of 8 cycle delay. The 8 cycle delay minimum is balanced with the minimum number of possible cycles to receive data from the L2 cache in the case of an L1 load miss. So table 18.3 gives the most common cases that can result in an instruction replay because of a memory system stall. To deal with these stalls, a recovery mechanism is used to flush all the subsequent instructions in the execute pipeline and reissue, that is, replay them. To support replay, instructions are copied into the replay queue before they are issued and removed as they write back their results and retire. For replay signal is issued, instructions are retrieved from the replay queue and re-enter the pipeline. The decoder unit issues two instructions in parallel to the execution unit unless it encounters an issue restriction. Table 18.4, which we're showing here, shows the most common restriction cases. And so you can pause the video and look over these tables in more detail, but I'm just going to continue on with what we're covering. So the instruction execute unit consists of two symmetric arithmetic logic units, that is ALU, pipelines, an address generator for load and store instruction, and the multiply pipeline. The execute pipeline also performs register write back. The instruction execute cycle, first we have the execute all integer ALU and multiply operations, including flag generations. Generate the virtual address for loads and stores and the base write back values when required. Supplies formatting data for stores and forward data for flags. Processes branches and other changes of instruction stream and evaluation instruction condition codes. For the arithmetic logic unit instructions, either pipeline can be used consisting of the following stages. So E0, access register file, up to 6 registers can be read from the register file for 2 instructions. E1, the barrel shifter. You might want to go back to figure 1425 to get some insight into that. So the barrel shifter performs its function if needed, and so keep that in mind. E2, the ALU unit performs its functions. E3, if needed, the stage completes saturation arithmetic used by some ARM data processing instructions. E4, any change in control flow, including branch mispredictions, exceptions, and memory systems replays are prioritized and processed. And then our E5, results of the ARM instructions are written back into the register file. Instructions that invoke the multiply unit are routed to pipe 0. The multiply operation is performed in stage E1 through E3, and the multiply accumulate operation in stage E4. Let's now talk about the load/store pipeline. The load/store pipeline runs parallel to the integer pipeline. The stages are as follows. E1, then the memory address is generated from the base and index register. E2, the address is applied to the cache arrays. E3 is the case of a load. Data are returned and formatted for forwarding to the arithmetic unit, or the MUL, the multiply unit. In the case of a store, the data are formatted and ready to be written into cache. E4, perform updates to the L2 cache if required, and E5, results of ARM instructions are written back into the register file. Here in table 18.5, it shows a sample code segment and indicates how the processor might schedule it. So once again, I'm not going to go through the details of this, but you're more than welcome to pause the video and look over this in more detail. Okay, let's look at the ARM Cortex-A8 Neon and floating point pipeline. A little bit more complicated here. So all SIMD and floating point instructions pass through an integer pipeline and are processed in a separate 10-stage pipeline, which we're showing here. The unit, referred to as Neon unit, handles packed SIMD instructions and provides two types of floating point support if implemented. A vector floating point VFP coprocessor performs floating point operations in compliance with the IEEE 754. If the coprocessor is not present, then separate multiply and add pipelines implement the floating point operation. So the preceding section looked at the rather complex pipelining organization of the Cortex-A8, an application processor. As a useful contrast, what we're going to talk about in this section will examine the considerably simpler pipeline organization of the Cortex-M3. The Cortex-M series is designed for the microcontroller domain. As such, the Cortex-M processors need to be as simple and efficient as possible. So in this figure 18.13, it provides a block diagram overview of the Cortex-M3 processor. This figure provides more detail than was shown in figure 1.16 back in chapter 1. Key elements include the processor core. It includes a 3-stage pipeline, a register bank, and a memory interface. The memory protection unit, this protects critical data used by the operating system from user application, separating processor tasks by disallowing access to each other's data, disabling access to memory region, allowing memory regions to be defined as read-only, and detecting unexpected memory access that could potentially break the system. They have the nested vectored interrupt controller, NVIC. It provides configurable interrupt handling abilities to the processor. It facilitates low latency exceptions and interrupt handling and controls power management. We have the wake up interrupt controller, the NVIC. It provides configurable interrupt. Sorry, I need to repeat that. Then we have the flash patch and breakpoint unit, and implements breakpoints and code dispatches. We have the data watch point and trace, the DWT. It implements watch points, data tracing, and system profiling. We have the system wire view. It can export a stream of software generated messages, data trace, and profiling information through a single pin. We have the debug access port. It provides an interface for external debug access to the processor. We have the implement trace macro cell. It is an application-driven trace source that supports the printf style debugging to trace operation system and application elements and generate diagnostic system information. And finally, we have the bus matrix. It connects the core and debug interfaces to external buses on the microcontroller. So the Cortex-M3 pipeline has 3 stages, which we're showing in this figure. We'll examine these in turn. During the fetch cycle, only 32-bit word is fetched at a time and loaded into a 3-word buffer. The 32-bit word may consist of 2 thumb instructions, 1 word-aligned thumb 2 instruction, or the upper and lower half word of a half word aligned thumb 2 instruction with 1 thumb instruction, or the lower / upper half word of another half word aligned thumb 2 instruction. All fetch addresses from the core are word aligned. If a thumb 2 instruction is half worded aligned, 2 fetches are necessary to fetch the thumb 2 instruction. However, the 3-entry prefetch buffer ensures that a stall cycle is only necessary for the first half word thumb 2 instruction fetch. The decode stage performs 3 key functions. Instruction decode and register read, the decode thumb and thumb 2 instructions. Address generation, the address generation unit, or AGU, generates main memory addresses for the load / store unit. Branch, it performs branch based on immediate offset in branch instruction, or a return branch on the contents of the link register R14. Finally, there is a single execute stage for instruction execution, which includes ALU, load / store, and branch instructions. To keep the processor as simple as possible, the Cortex-M3 processor does not use branch prediction, but instead uses a simple technique of branch forwarding and branch speculation defined as follows. Branch forwarding, the term forwarding refers to the presence of an instruction address to be fetched from memory. The branch forwards certain branch types by which the memory transaction of the branch is presented at least 1 cycle earlier than when the opcode reaches execution. Branch forwarding increases the performance of the core because branches are a significant part of embedded controller application. Branches affected are program counter relative with immediate offset, or use the link register LR as the target register. For branch speculations, in the case of conditional branches, the instruction address is presented speculatively so that the instruction is fetched from memory before it is known if the instruction can be executed. Cortex-M3 processor prefetches instructions ahead of execution using the fetch buffer. It also speculatively prefetches from branch target addresses, specifically when a condition branch instruction is encountered. The decode stage also includes a speculative instruction fetch that could lead to faster execution. The processor fetches the branch destination instruction during the decode stage itself. Later, during the execute stage, the branch is resolved and it is known which instruction is being executed next. For branches not to be taken, the next sequential instruction is already available. The branches to be taken, the branch instruction is made available at that same time as the decision is made, restricting idle times to just 1 cycle. We're showing in this figure that it clarifies the manner in which branches are handled, from which can be described as follows. The decode stage forwards addresses from unconditional branches and speculatively forward addresses from conditional branches when it's possible to calculate the address. 2, if the AL unit arithmetic logic unit determines that a branch is not taken, the information is fed back to empty the instruction cache. 3, a load instruction to the program counter results in a branch address to be forwarded for fetching. So as can be seen, the manner in which branches are handled is considerably simpler for the Cortex-M than the Cortex-A, requiring less processor logic and processing. Okay, well, just to finish up here, we're seeing some really amazing complexity and stuff that has been thought through for quite some time. And so we got a chance to be looking at the super scalar and super pipeline type of architectures, and we did a comparison between them. We looked at the design issues that come up, the instruction level parallelisms, machine parallelism, instruction mission policy, register renaming, branch prediction, super scalar execution, and super scalar implementation. We looked at the Intel Core microarchitecture and found out that here we have a CISC, complex instruction set computing, using a RISC construction underneath the hood as they've matured. And so there's like levels of the architecture that you can be thinking of. So it has a RISC microarchitecture below the architecture. Then we spent time first looking at the ARM Cortex-A8, which is a more involved and elaborate types of processor in the ARM family. And then we talked about the ARM Cortex-M3, which is used as a microcontroller, very simple type of processor in comparison. All right, well, that will end it for now. Thank you very much.